Hey everyone, and welcome back to The Explainer. Today, we are officially entering what I like to call the builder's arc of machine learning. If you've been following along with us, you know we've already looked at what machine learning actually is and how we go about prepping our data. But here in Unit 4, well, we're finally rolling up our sleeves and building. We're going to tackle 3 completely different, yet absolutely crucial stages of the machine learning lifecycle. We'll look at how to find structure in total chaos when we have 0 labels, how to force weak predictive models to team up and become absolute powerhouses, and finally, how to audit their work and measure their errors. It is a packed, super fascinating unit, so let's just dive right in. Okay, here's our roadmap for Unit 4. We'll start with a welcome and then jump into clustering with k-means. From there, we'll look at the power of ensembles, followed by a specific method called boosting weak models, and we'll wrap the whole thing up with measuring model errors. Section 1. Clustering with k-means, finding patterns in the chaos. So picture this. You've got a massive spreadsheet of customer data, right? Maybe it shows their ages and their incomes, but you don't know who the premium customers are or who the bargain shoppers are. You don't have any predefined labels or answer keys. How do you actually make sense of that data? Well, to solve that, we use unsupervised learning. Now, notice the contrast here. In supervised learning, which is what we usually hear about, you have an answer key. Every input has a known correct output label, and you're basically training the algorithm to map the input to the answer. But unsupervised learning, that's a completely different beast. It explores patterns and associations in unlabeled data entirely without external supervision. There's literally no answer key. There's no teacher standing there saying, yes, that's a cat, or no, that's a dog. The algorithm is just fed raw data and asked to discover the underlying structure, the patterns, and the groups entirely on its own. It's pretty amazing. And this brilliantly illustrates exactly what we're trying to achieve here. If you look at the before k-means setup, it's just a scatter plot. It's really just a bunch of dots floating around in a two-dimensional space. I mean, to the human eye, you might be able to sort of guess at some groupings, but to a computer, it's just raw x and y coordinates. It's disorganized, it's total chaos. But then look at the after k-means state. The algorithm has magically partitioned those dots into 3 neat, distinct, organized groups, complete with a center point for each. It figured out how to assign each data point to a cluster based on its commonalities. In this specific case, its physical distance to the other points. It successfully separated the signal from the noise. But you're probably wondering, how exactly does it pull off this magic trick? Well, it does it through this brilliantly simple, repetitive loop. Let's walk through these steps together exactly as they're laid out in our syllabus. Step 1. You, the human in the loop, have to select the number k, and k is simply the number of clusters you want the algorithm to find. In that last example, k was 3. Step 2. The algorithm drops k random points onto the graph. We call these centroids. You can think of them as the initial, totally random leaders of our new clusters. Then we hit Step 3. Every single data point in your dataset looks around and asks, hey, which centroid am I closest to? And it assigns itself to that closest one. Now, Step 4 is where the actual learning happens. Now that we have these rough, kind of messy initial clusters, the algorithm calculates the variance. It finds the actual, true, mathematical center of all the points in that newly formed cluster, and it literally moves the centroid to that new center. Now we hit Steps 5 and 6, which is the loop. Because those centroids just shifted, some data points might now actually be closer to a different centroid, so they switch teams. Then we calculate the new centers again, we move the centroids again, and this just repeats over and over until nothing changes. The centroids stop moving, no data points switch teams. When that happens, as Step 7 tells us, we're completely done. The model is ready. It's just this elegant trial and error geometric dance that takes chaos and turns it into clean, usable clusters. Section 2. The power of ensembles. Teaming up for better predictions. Okay, so imagine you build a predictive model. Maybe it's a decision tree, but it's kind of weak. It makes mistakes. Instead of just throwing it in the trash, what if you built a whole team of weak models? That right there is the core philosophy of ensemble methods. As our source materials state, an ensemble approach combines predictions from multiple individual models to achieve better predictive accuracy and robustness than any single model could on its own. Think about it like asking a giant crowd to guess the weight of a cow at a fair. One person might be way, way off, but the average guess of 100 people, it's usually shockingly accurate. In machine learning, instead of relying on one single overly complex model that might just memorize the data and overfit, we use several weak learners. By aggregating their outputs together, we reduce errors, we minimize variance, and we create a highly robust super team. It's a real game changer. Section 3. Boosting weak models, learning from mistakes. Now, within this world of ensembles, which includes other cool techniques like bagging and random forests, There is one incredibly powerful technique we absolutely need to focus on, and that is boosting. Boosting takes that team concept we just talked about and adds a brilliant twist to it. It's an ensemble technique that attempts to build a strong classifier from a number of weak ones. But here's the secret sauce. It builds them in series. In a lot of other ensemble methods, you might build, say, 100 models independently at the exact same time. But boosting, it builds them sequentially, one after another, with a highly focused purpose, to correct the specific errors made by the model that came right before it. Let's detail exactly how this sequential process plays out. Step 1. A first model is built from your training data. Now, because it's a weak learner, it's going to get some things right, for sure, but it's going to get a lot of things wrong. Step 2. The algorithm identifies exactly which data points were incorrectly predicted by that first model. Step 3. A second model is built, but this one acts like a specialized tutor. It doesn't just look at the whole dataset equally. It focuses extra weight and extra attention on the exact errors of the first model, trying its absolute hardest to get those specific tricky points right. And then, step 4. We just continue this procedure. A third model focuses on the second model's errors, a fourth on the third, and so on. These models are chained together in this way until the complete training dataset is predicted correctly or until we hit a maximum number of models that we set. By learning directly from its past mistakes and weighting those errors heavily, the ensemble literally boosts its way to incredible accuracy. Section 4. Measuring model errors, grading the performance. All right, so we've clustered unlabeled data, we've built highly accurate sequential boosted models, but here's the thing about machine learning. You never, ever just assume a model works. You have to grade its performance on unseen testing data. Our syllabus gives us a veritable toolkit of evaluation metrics to use for this exact purpose. I'll rapidly list them out here just so you know what's in the toolbox. We have accuracy, which is simply the total percentage correct. We have the confusion matrix, tracking our false positives and false negatives. From that matrix, we get precision, recall, and their combined harmonic mean, which is called the F1 score. We also have graphical tools like the receiver operating characteristic curve, or ROC, and the area under the curve, the AUC. And finally, we look at the overall distribution of errors. All of these metrics tell us different, really important stories about where our model succeeds and where it falls flat. So the crucial point here is understanding the spread of those errors. And that leads us to zero in on one specific metric detailed in our sources, MAD. This can stand for median or mean absolute deviation. Let's focus on the mean absolute deviation for a second. MAD is defined as the average distance between each data point of the dataset and the mean of the data. Now, what is this actually telling us? Essentially, it represents the amount of variation that occurs around the mean value. It's a measure of spread. If your model's errors have a high MAD, it means your predictions are wildly scattered all over the place. Not great. But if the MAD is low, your errors are tightly clustered together. It tells us how consistent our data, or our errors, really are. Okay, don't let the math symbols scare you off here. MAD equals the sum of the absolute value of x minus mu, all divided by n. I know, it looks like a completely foreign language, right? But it's essentially just a really simple recipe for calculating an average distance. Let's decode exactly what these pieces mean because it's actually super straightforward. Let's walk through these variables like puzzle pieces. First up, mu, that's that little U-shaped symbol, is simply the mean, or the average of your whole dataset. X represents each individual observation or data point. So the core of the formula, x minus mu, is really just asking, hey, how far away is this single point from the average? We use absolute value bars, those straight vertical lines you saw, because we only care about the actual distance, not the direction. Being 5 units above the average or 5 units below the average is still just a distance of 5. Next, the sigma symbol just means we add up all those individual distances. Finally, you divide by n, which is just the total number of observations. So when you put it all together, you're literally calculating the distance of every point from the average, adding them all up, and dividing by the total. It is simply the average of the distances. It's a beautiful, remarkably simple way to measure spread. Section 5, the big picture, Unit 4 recap. And just like that, we've completely traversed the builder's arc. We covered a ton of ground and conquered 3 massive concepts today that fit perfectly into the machine learning workflow. First, we learned exactly how to find hidden patterns in complete chaos using unsupervised learning, watching k-means drop its centroids and loop its way to perfectly organized clusters. Second, we learned how to build predictive superteams with ensembles, specifically looking at how boosting hyperfocuses on correcting past mistakes to create incredibly strong, robust models. And finally, we learned that we must always measure our success, looking at our toolkit of evaluation metrics and breaking down the math of the mean absolute deviation to really understand the spread and variance of our errors. But before we wrap up, I want to leave you with a thought, a little warning to chew on as we prepare for whatever comes next. Earlier, we said that boosting builds models in series until the training data is predicted perfectly. But really think about that for a second. If a boosted ensemble memorizes its training data so perfectly by endlessly obsessing over every single tiny error, what happens when it encounters an unpredictable, totally new environment? Does it actually generalize well to the real world, or has it just memorized the past? That right there is the dangerous trap of overfitting, and it's something every single machine learning engineer has to battle. Thank you so much for joining me on this deep dive into Unit 4. Keep questioning, keep building, and I will see you in the next explainer.